Yeah. Sorry. Yeah. Okay, so what we've done so far is we started off by saying that okay, you can have a set which may have non-measurable sets, so sets which you can't assign countable additive measure on translation invariant sets. Then we said okay, let's assign measures on a sigma algebra. So we'll on a rich class of sigma algebra. So the point was, how do we do this? So we started with an algebra, and we defined an outer measure on it. And then we constructed a collection of sets which we showed was a sigma algebra, on which include the algebra inside it. The measure on the algebra agreed with the outer measure, so that was good. And the outer measure on the remaining sets on the remaining sigma algebra were also uniquely defined. So, well, uniquely defined, no, but they were defined. And now we'll prove the uniqueness result. That's kind of where we ended last time, that we had not, and I guess, yeah, the uniqueness proof is somewhat involved. It's not as simple as I was hoping. I mean, there are a number of proofs, but this proof is nice. So you get exposed to some other ideas. So it's a little bit more involved. So suppose P1 and P2 are measures on omega, and so Shantanu, will you be turning your camera on? If you can, it'll be a good idea. If you can't, that's fine. So we have the space omega and sigma algebra F on it, and now we have two measures P1 and P2, which agree on pi 0. Now pi 0 is a pi system, so it's not even an algebra. It's just a system which is closed under intersection. So if A and B are in pi 0, then A intersection B are also in pi 0. Right? So it's a pi system. I should have written that here, but that's another. That's what we have. And then F is a smallest sigma algebra which contains the set pi 0. I somehow thought maybe I mentioned it later. So think of pi 0 as just being half lines. Minus infinity to A, closed interval. Then if you take the intersection, it's closed under intersections. And the smallest sigma algebra, which includes all these half lines, you can see, if you haven't already, that's just the Borel sigma algebra. Smallest sigma algebra that contains the open sets. So we're okay, we're good to go. That's okay. So now if we have P1 and P2 which agree on the pi system, then they agree also on the whole overall sigma algebra. So that's the result. Because in that sense, the extension where it's there is unique from pi 0. I mean, algebra is definitely a pi system. So from an algebra to the sigma algebra, the extension, if it exists, is going to be unique. This is for finite measures. So what we need to do for this is we first need to define a D system. So we need some notation, but it's a good system to have. So it's a collection of sets, again, from our space omega. I'm going to call it calligraphic D. So it contains the overall space. And if A and B are there and B dominates A, then B minus A is also in D. Right? So differences are in D basically. If B and E are not related to each other, then we're not saying anything. I mean, if B does not include A, then we're not saying anything. But if B includes A, then B minus A is also in D. And if AN is in D for each n, and AN is an increasing sequence of sets, so it's getting larger and larger, then its limit. What is the limit? What's the limit of AN in this case? Anyone? How do we define it?
Union.
It's just a union. That's a well-defined object. So union is A, so then A must also be in D. So so this D collection has these properties that differences between sets are there, and if you have a set of increasing sequence of sets, then the limit is also there. Okay, so this is it's an easy class to kind of show membership of, and then with some more properties you get to say that okay, this class is also a sigma algebra. Right now it's not a sigma algebra. For proving U, I guess I must have defined. Surprised for how happened these notes. Yeah, U must be this result, I guess. Yeah, this is U, sure. Define calligraphic C class, which is like we had last time, all the sets in A where P1A is equal to P2A, right? Later, we'll argue that this class is actually equal to F, right? So right now it's a subset of F. Later we'll show it's actually equal to F. So first we'll argue that C is a D system, right? If A is subset of B and A and B are in C, calligraphic C, then clearly B minus A is in the calligraphic C, because P of B, P1B is equal to P2B, P1A is equal to P2A, and P1B minus A is just P1B minus P1A. P2B minus A is P2P minus P2A. So B minus A is certainly in this calligraphic C. So we'll just show basically that this calligraphic C class is a D system. It's not yet a sigma algebra. For it to be a sigma algebra, this D system will have to be a pi system. So that's a result that we'll show in a moment. That if a D system is also a pi system, that it includes a sigma algebra containing the pi system. So yeah. So then it'll become a sigma algebra basically. So we just need to show it's a pi system. All right. Then it's also a pi system, I guess. Yeah. All right. So, and if AN is in calligraphic C and AN is increasing to A, right? Then P1 AN and P1 AN is equal to P2 AN. Then are we missing some students right now? I know Saurav is one, but is anybody else missing? Should we just?
Agniv is going to join later. Like,
but there's no confusion about time, at least, right?
No, he doesn't have confusion. Actually, he's kind of busy, but he will like.
Okay, good.
That's all.
Yeah. We're not used to people not joining in this NTF. Okay. Yeah, that happens in some other kind of colleges. All right. So yeah, so if P1AN increases to P1A and P2AN increases to P2A, then we know that P1AN is increasing to P1A, right? By countable additivity or probability measure, if AN is increasing to A, then probability measure evaluated AN is increasing to probability of A. System limit. Just by countable additivity, it's easy to see. So P1AN is increasing to P1 of A, P2AN is increasing to P2 of A, then P1A and P2A had better be equal, right? They can't be different anymore. Because P1AN is equal to P2AN, so the limits cannot be different, otherwise you have a contradiction. And I suppose the limits are different, then of course you can show that there must be some n for which P1AN is not equal to P2AN. All right, yeah, so our calligraphic C is a D system. Here's that we've seen. Then we'll show that D of pi 0 is a pi system. Right. I may have not put some steps in between now that I think about it. So D of pi 0 we'll show is a pi system. Right? Pi 0 itself is a pi system. And we are saying D of pi 0, smallest D class, which includes pi 0, is also a pi system. Right? Yeah, that I was teaching today must be correct, but it just doesn't sound right. So D1 is, let us collect all the sets B in D of pi 0. So let's look at D of pi 0. It's the smallest D system which includes the sets in pi 0. Okay. So let's include all the sets B in D of pi 0 such that B intersection C is also in D of pi 0 for all C in pi 0. So let's absorb this definition for a moment. So we look at, so we know, for example, all the sets in pi 0 will be members of this, right? Because pi 0 is closed under intersection. So B intersection C will be in pi 0 for all C in pi 0. So in particular, it will be in D pi 0 for all C in pi 0. So this class is going to include pi 0 in it, this class D1. And our claim is it's actually a D system. So then it becomes equal to D pi 0 because it's a D system, subset of D of pi 0 by definition. And it's at least as big as D of pi 0 because it's a D system which includes pi 0. So we just have to argue that this system is actually We have to argue that this system is actually a D system. So let's go step by step. Let's take A and B in D1. We have to show it's a D system, right? So we'll take two sets A and B, and A, let's say, subset of B. And now we'll simply argue that, okay, B minus A must also be in this class D. Okay, so basically, so let's take, C in pi 0, right? Okay, so let's see. So A and B are in D1, right? That means A intersection C is in D of pi 0 for C in pi 0, and B intersection C is in pi 0. In D of pi 0 for C in pi 0, right? By definition. So then you look at B intersection C minus A intersection C, right? So that's going to be in D of pi 0. Because D of pi 0 is closed under, the subtraction operation, right? So B intersection C minus A intersection C is in D of pi 0. And that means B minus A, B with A subtracted from it, intersection C is also in D of pi 0. These two sets are the same. B intersection C minus A intersection C. So it's basically what? B union, B common with C, B intersection C common with A intersection C complement, right? That's what this is. B intersection C common with A intersection C complement. That's what B minus A means. And this part is nothing but A complement union C complement, right? What did we have? We have C complement, sorry. And this you can see is equal to B common C common A complement. Right? Because C complement and C won't have anything in common. So you might as well not have it there. You get nothing more from having C complement there. And this is nothing but, sorry, have I written something wrong? Yeah, no, I think I've written wrong. And this is nothing but B minus A intersection with C. Right? B common A intersection with, B intersection with A complement, that's B minus A intersection with C. So that's exactly this guy here. So this guy is in D of pi 0. Okay, so what that tells you is that B minus, and this is true for every C in pi 0. So B minus A also belongs to your class calligraphic D1. Right? This is, we want to show membership.
I have a doubt. This B intersection C minus A intersection C is belonging to D of pi naught. So are we assuming that D of pi naught is already like existing?
Yeah. So D of pi naught is the smallest D class which includes pi naught.
But we have to show that D1 is a pi system, right? That D1 is equal to D of pi 0.
So D1 we have to show, but D of pi naught is already a D system.
Okay.
D1 we have to show. Yeah. So what's the confusion here?
So we concluded that B minus A intersection C is in D of pi 0. That is fine. Okay.
Yeah. For all C, so B minus A intersection C in is in D of pi 0 for all C in pi 0. So that's a membership criteria for D1. So that tells you that B minus A is in D1. But to your question, D of pi 0 was already a D class. So for any two sets where one set is bigger than the other, the difference is in that set. Okay, so we've got this B minus A is in D. What are the other criteria that we need for D1 to be a pi system? No.
increasing sequence going.
Increasing sequence you need to show.
Yeah. No.
So for pi system, intersection.
No.
For D
So,
system, increasing.
D system.
Yeah, it's a D system. Sorry, I'm not sure what I was thinking, but this should be a D system. Of course, now I'm correcting in a PDF copy, but it's a D system is what you're going to show. So you'll see, when I share it with you, I'll probably have errors inside it. So it's equal to D of pi 0 is what you want to show, basically. Okay. That's where you want to go. Okay. So now you'll see, okay, AN is increasing to A, and all the ANs are in D1, let's say. So now we want to say that A is also in D1, right? So AN is in D1, that means AN intersection C is in D of pi 0 for all C in pi 0, right? That's what the membership means. Okay. Now this would imply that A intersection C, AN is increasing to A. A intersection C is also in D of pi 0. Right? Right, because AN intersection C is increasing. So the limit will, because D of pi 0 is a D system, the limit will also belong to D of pi 0. So A intersection C belongs to D of pi 0. And that for all C in pi 0. So that means A is also in D1. So your D1 is equal to D of pi 0. Right? That's what we want to show. That your D1 is equal to D of pi 0. Is this clear to all? I mean, I guess you need to show that omega is in D1. That's one more thing you have to show. But that's easy to check. No, because let's just go back to D1. So it's all, so omega is in D pi 0. So omega intersection C should be in D pi 0. That's trivially true. Okay, so we've shown now that D1 is, this is what we wanted to show. So we've shown that D1 is equal to D of pi 0. Okay. What we wanted to show was, basically we wanted to show that D of pi 0 is a pi system. That's where we want to go. And what we've achieved right now, we've shown that D1 is in D of pi 0. Okay. Now what we'll do is, we'll define D of 2. So it's a little clever proof. It's again, it looks like it's almost circular, but it's not. Now we'll define D2. So these are now all the sets A in D of pi 0, such that A intersection C is in D of pi 0 for all C in D of pi 0. So we've changed the definition now. Now we're not keeping C to be in pi 0 here. We are keeping it for all C in D of pi 0. So now if we can show that D2 also, by same logic, if we can show that D2 is also equal to D of pi 0, we've shown that D of pi 0 is a pi system. Right? Because all the elements in D of pi 0 intersected with all the elements in D of pi 0 are in D of pi 0. So that's what it becomes a pi system. Yeah, so it seems like it's it's a bit of a machinery, and somehow you would have imagined that maybe the proof would have been simpler. So I don't really have an intuition as to I'm not spending enough time with this at all to say more on this, why this is a good way to prove things. But nonetheless, it's good to see this. So now we'll do the same thing, right? So yeah, if D2 is equal to D of pi 0 implies that D of pi 0 is a pi system, which is what we want to show. So we want to show D of pi 0 is a pi system. All right. Okay, so again, consider A and B in D2 where A is smaller than B. Then again, B intersection C minus A intersection C is in D of pi 0 for all C in D of pi 0, right? That's again by the membership criteria, So A intersection C, since A and B are in this, that means A intersection C and B intersection C are in D of pi 0 for all C in D of pi 0. right? And again, this means that B minus A intersection C is in D of pi 0 for all C in D of pi 0. So B minus A is a member of D2 whenever B is bigger than A, right? Okay. Similarly, again, if AN is in D of 2 and it's increasing to A, then again, exactly by the same reason, AN intersection C is in D of pi 0 for all C in D of pi 0, and AN intersection C is going to increase to A intersection C for all C in D of pi 0. So A is going to be member of D2. Right? So that means D2 is closed under kind of this increasing sequences. Right? So D2, and again, pi omega is going to be in D2. That's an easy check. So our D2 is a D system, and hence it's equal to D of pi 0, and hence D of pi 0 is a pi system. So now we've shown that D of pi 0 is a pi system. It's also a D system. It's a small proof to check that if something is a pi system and a D system, it's a sigma algebra. I don't know if I show. Oh yeah, I've shown this. I was worried that I forgot to put this. So D of pi 0 is equal to sigma. So sigma pi of 0 is of course D of pi 0, right? If you have a sigma algebra, it's closed under intersection, so it's a pi system. And B minus A is going to be there for every B and A. And if you have an increasing sequence, its limit is going to be there. So sigma algebra is obviously a D system. But the interesting part is that D of pi 0 is actually equal to sigma algebra. If D of pi 0 is a pi system, then you get it to be a this thing. So that's a clever way of showing that what we have is actually a sigma algebra. So how do we check this? Well, if A is in D of pi 0, then we want to first of all argue, because we want to show it's a sigma algebra, right? So we want to show that, okay, A complement is also in D of pi 0. And why is that true? Anybody? So let's just go a little slow. So why should A of complement be in D of pi 0? What all do we know about D of pi 0? It's a D system and it's a pi system.
Omega minus A.
Shadnu, go ahead.
Omega minus A.
Omega minus A, absolutely. Right? Omega is bigger than A and omega minus A, that's all. All right, so A complement. And given A1 and A2 are in D of pi 0, arbitrary A1, A2 now. Their union should also be in D of pi 0, right? For it to be a sigma algebra. Why is that the case?
You can create increasing union by B2 equal to A1 union A2, B3 equal to A1 union A2 union A3. So it is increasing union, and this should belongs to.
Exactly. So you can take Bn to be the union of first n events. Then this is an increasing sequence, and its limit is exactly the countable union of the AIs. Hence, the countable union of AIs also belongs to your D system. And hence, it's a sigma algebra. Right? So then now we are done, basically. So essentially what we've shown then is that the two measures which agree on an algebra, agree on the smallest, well, agree on a pi system, agree on the smallest sigma algebra, which contains that pi system. Okay, so we have the uniqueness. Okay. So big picture is, so we've got a lot of work done already in some sense, right? All we really need to do now is assign probability measure to an algebra, and then it will extend nicely to the whole sigma algebra. So we don't have to worry about any contradictions anymore. And sigma algebra is pretty big, and we'll see some examples to illustrate why sigma algebra is actually a huge quantity. So one doesn't really have to think outside sigma algebra in many settings. So now we can assign probability to an algebra in R. So for example, collection of finite union of intervals, we know how to assign probabilities to this, right? If you have a PDF, we know how to assign probability to every interval and hence to every finite union of intervals. If it's a PDF and a point master somewhere, then also we can do that, right? And for most purposes, that's enough. One doesn't have to worry about more general probability measures. So this should be enough. I mean, I don't see that there'll be a problem more generally, but one just never deals with more general settings. And then it gets uniquely extended to the sigma algebra, Borel sigma algebra. the smallest sigma algebra which contains all the intervals or all the open sets on the real line. Okay. Okay, now we want to extend it to B of R square. So we know how to, so at least conceptually, we know how to assign a measure to Borel sigma on the real line. How do we assign a Borel sigma to R square now? So let's just talk about that as well. So we'll assign probability to each rectangle I1 cross I2 intersection of intervals. And again, intervals, we won't worry about whether, the last element is there or not. They were considering all possibilities. Closed interval, open interval, sub-closed interval, sub-open intervals, all of this. Intersection of such intervals, because we know that finite union of such intervals is going to be if you collect all those finite unions, we have an algebra. Yeah, that you can check. Okay, so we can assign, so that's a big picture. We can assign, probability to this algebra, and then we're hoping Cauchy-Doury's theorem will extend it to B of R2, the smallest sigma algebra which contains all these rectangles. So one interesting point to see is as follows. It clarifies things. Yeah. So this sigma algebra, which is the smallest sigma algebra, which contains all the rectangles, or you can even say open rectangles, right? That can be a definition. Actually is equal to BR product with BR, product of those two sigma algebra. So what do I mean by this? I mean smaller sigma algebra that contains B1 cross B2 for all B1 and B2 which are Borel sets, right? So clearly this is going to be bigger, right? Because this already contains all the intervals. And then one can argue that it's actually going to be, the two sigma algebras are going to be the same. So we'll do that right now. We'll just look at that argument too. It's again, these are things which after a while but it's good to see it done cleanly. So is this clear what we are saying? We have these rectangles and we have the smallest sigma algebra which contains all the rectangles. And we have other way to construct these smaller sigma algebra, which is through taking the product of Borel sets and smallest sigma algebra which contains these products. So both these collections we are saying are going to be equal. Clearly one is bigger than the other. We just want to show that that's also smaller than the other. Okay, so we'll collect all sets of the form. So this is my new argument from the morning, and I think it's correct. It's motivated by the earlier argument. So all B such that, so I'll call this calligraphic set A as all sets B such that B cross I is in BR square for all I in BR square. For all I in, for all I basically, for all intervals I. For all intervals I, that's what I mean by this notation. Okay. The point is, clearly this calligraphic A contains all the intervals because intervals cross intervals are in BR square. That's how we got this. Okay. And it contains the overall real line. The real line is also an interval. So we're going to argue that this calligraphic A is actually a Borel sigma algebra.
So in A, B is the Borel set, right? B in Borel of R, or any subset of.
Yeah, I think we should. Yeah, I was thinking about that right now. Might as well keep it in Borel. You can unnecessarily get unpleasantness otherwise. So let's just avoid and I can't change it. Sorry. B in Borel R. Otherwise, you might get a bigger sigma algebra, and it might cause problems somewhere technicality. So I've not thought that through. So let's just keep it simple by keeping it this way. So A is all B in Borel sigma algebra R, so that B cross I is in BR square for all I, for all intervals I. I could have given a notation to this, but that's fine. All I belonging to calligraphic intervals I. Okay. Okay, so if B is in A, then B complement is in A. So let's just go back on what does, just make sure that we get this right. So what do we want to show? That B complement I is in BR square for all I. Right? That's what we need to show. So B complement I is nothing but R cross I minus B cross I. Now think of, I guess, a rectangle here. Right, I'm going to keep this. Let's say this is my I. this is my set B, then this set here, well, complement of this set here is this whole strip minus this set, right? And right. So R cross I is in my set and B cross I is in my set. Right. And we are a sigma algebra, right? Both these sets are a sigma algebra, so the difference is also there. Okay. Now, if A1, A2, and so on are in my calligraphic set A, then their countable union is also in my calligraphic set A. So again, let's get back to the definition. So that means A1 cross I, A2 cross I, and so on are all in my sigma algebra, right? For every I. Okay. And if I take the union, that will also be in my BR square in my sigma algebra. So this is going to be, this times I is going to be in BR square for all I. So that means I have my calligraphic A is closed under countable unions. So it's a sigma algebra. Okay. So my calligraphic A is a sigma algebra, and it's actually going to be equal to, because it contains all the intervals, it'll be Borel sigma algebra. It's a subset of Borel sigma algebra. I kept it that way. And now it is a sigma algebra, so it's a Borel sigma algebra. Because it's a sigma algebra which contains all the intervals, so it's at least as big as B of R, but it's also smaller than B of R, so it's equal to B of R. Okay, so A is B of R, that's where we are, right? Now define D, so we'll again carry on in the same manner. So we'll define D to be all the sets A, right? So that B times A is in BR square for all B in Borel sigma algebra, right? And by the same argument, we'll get that this D is also going to be a sigma algebra. Oh, and again, as Shubhata pointed out, let's keep this in the Borel sigma algebra R. Otherwise, you might get something bigger. Right. So then after this, we are done, right? If once we show that D is a sigma algebra, Borel sigma algebra, that means B1 cross B2, where B1 and B2 are in Borel sigma algebra, belong to my BR square. Right? And that's what I wanted to show. My objective was to show that, okay, B1 cross B2, when they're Borel sets, they belong to my, I guess they're members of R square. Now, this is a sigma algebra. All these guys are in there. So smaller sigma algebra, which contains all these also there. That would imply that B of R cross with B of R is also a subset of B of R square. And hence the two are equal. Because B of R square was in any case smaller than this product sigma field, sigma algebra, sigma field. Okay, and this is going to be exactly the same argument. Should work, I hope. So again, R is in D, right? Because B cross R is going to be in BR square. We just showed that. If A is in D, then A complement is in D. So if A is in D, that means B cross A is in BR square for all B in the Borel sigma algebra, I guess. So that means B of A complement is also in the B cross A complement is, because B cross A complement is again B cross R minus B cross A. So B cross A complement is also going to be in my Borel sigma algebra, BR square, for all B in the Borel sigma algebra. So A complement is also in D. And now we are doing exactly the same thing, A1, A2, and so on. So B cross AI is in D for all I, for all B in BR. This implies that, okay, B cross, because this is just an intersection basically. When we take a product set, it's basically intersection of two sets, right? B cross real line intersect with R cross AI. So B cross union of AI is also going to be in D. So BR square contains B1 cross B2, and hence BR square is equal to BR cross BR, the product measure corresponding to sigma algebras on the two real lines. Okay, and then you can generalize this to Rn. So that I'll let you do. But everything generalizes, you can proceed inductively. I mean, this should have variety of different proofs that I've shown you right now. Okay, so now, so we can show that B0Rn, so let's call B0Rn, because you can also say that why are we defining sigma algebra in Rn by using rectangles? Why not define it as a smaller sigma algebra that contains open sets, which is the spirit of Borel sigma algebra definition, right? Borel sigma algebra is smaller sigma algebra which contains all the open sets. So let's define it in that manner. So B0Rn is a smaller sigma algebra generated by the open sets, and these open sets are given as follows. So these are, I mean, open intervals right now. Same thing, you can always show, right? The smallest sigma algebra in Euclidean space generated by open sets is same as the smallest sigma algebra generated by all the intervals, by balls. Because you can always take a open set and cover it by, express it as a union of countably many balls. Right, so a sigma algebra which contains all the balls will contain all the open sets. And since it's a sigma algebra, it will contain the smallest sigma algebra which contains all the open sets. So that will work out. And if open sets include balls, so I mean, no issue there. That part is quite straightforward. Okay, so B0Rn is the smallest sigma algebra generated by open sets. So what I mean by that is, I fix an x0 for every point x0 in Rn. Each and every point x0 in Rn, I'll take a row here, and I'll collect all the points x which are within the ball Rn x0. Except in this case, I'm giving you a slightly funnier kind of a metric here. It's not kind of uniform weighing of distance or Euclidean R2 distance. Euclidean L2 distance, let's say. This is going to be our row 1 distance in one dimension between xk and xk0. Weighed by, this should be 2 to the power minus k, sorry. K equal to 1 to n. And the reason I'm defining this decaying with 2 to the power minus k is because this definition will carry over when we go to infinity. When we go to infinite dimension.
So it's like trying to make sure the whole thing has a finite volume.
That's right. Yeah, exactly. Yeah. So then whatever we discuss in finite settings, in your homework, you can discuss in the infinite settings. Right? So that's kind of the thing. This is the common homework problem, so I will be giving you. Okay, right. And then you can argue, so now we got another sigma algebra, right? Corresponding to these things. And the question is, how does this relate to the one corresponding to rectangles? And the answer is again going to be the two are similar. Right? And how will we show this? We'll show, so how will we show this? Anybody? What would be a good way to think about this if you have experience with these things? I've given you some hints already. So yeah, I mean, I think once you need to see this idea cleanly, and then it becomes very clear. But it's important to see this one. So let's just do this once. So if I show you a rectangle, and let me keep it open on all sides. Right? Without loss of generality, I can consider rectangles which are product of open intervals. Right? Because once I have that in my sigma algebra, I can get all the other sets with it by intersecting countable intersections or countable unions. So that's not an issue. You see what I'm saying, right? That, I mean, I think most of you already know this, but A common B intersection is equal to intersection of A plus A common B plus 1 by n equal to 1 to infinity, right? So if I have open intervals, I also have this open and closed intervals. And similarly, I get closed intervals on both sides. Now I'll take these sets and I'll do the same thing with them. And I'll show that my sigma algebra contains closed intervals. If it contains open intervals, it should contain closed intervals too. The same thing you can do in 2 dimensions and talk about all rectangles. If the boundaries are missing, you can always, that's if the sigma algebra only contains open intervals, it has to also contain closed intervals, or some parts of boundary are missing, some parts of boundaries are there. So that's going to be a straightforward argument. Okay, so let's just look at these sets right now, which are open on all sides. And now the claim is I can embed inside them countably many balls which cover them. Balls from the other metric. Right? I mean, all that 2 did was it made the shape of the ball as an ellipse. So where I had 1 by 2, I could go twice as far, and I moved the same distance as where I did not have that 1 by 2. So you give an ellipse. Now what you do is, what I want to show is that I have countably many balls whose union is equal to this rectangle. So that means a sigma algebra which contains all the balls also contains all these rectangles. And hence it contains a smaller sigma algebra which contains all these rectangles. So everybody with me on this? That's the generic idea you're going to see everywhere. Okay. So what will I do here? How will I get this rectangle to be a union of all these balls? Any suggestions? I want to show it to be a countable union of these balls. I can go through all the rational points in this ball and all the rational radii so that the ball is inside this rectangle. And that union you can show is a subset of the ball, because each set is a subset of the ball, but also contains the ball. It's, each and every point in the ball lies in that union. Right, so I'll just show this. So take a union over all S rho x0. X0 belongs to this set A. I'm calling this set as A right now. Right? And it's rational. And rho is also rational. And S rho x0 is in A. That's a membership limitation. I keep that limitation. Right? These are well-defined things. So I'll just look at this integral here. No, this union here, countable union here. Since each S rho x0 is a subset of A, this overall union is also going to be a subset of A. And now you can argue any point in A is going to belong to some S rho x0. So it's equal to A. Okay, so everybody's with me on this, right? These are things you should just see once, and then you kind of know how to do it next time around. So you get, okay, B0 R square is at least as big as B of R square. Right? Now the other way around. Now we can do this, right? If I give you a ball, open ball of S rho x0, I can embed inside it rectangles, open rectangles. Again, I look at all the rational points inside the ball and all the widths of the rectangle, so that which are rational, so that I'm inside this ball basically, right? And I mean, this is all because I'm dealing with rational, I guess, what do I want to say? Rational product of rational, the rational is again rational, is again countable. You take another product, it's again countable. So A1, B1 cross A2, B2, so that I lie in this ball, S rho x0. A1, A2, B1, B2 are rationals. Yeah, so that's it. So I look at Yeah, and I'll take a union over all A1, A1, A2, B1, B2 with this, and that's going to be equal to S rho X0. So then I'm done basically, right? Yeah. Yeah, it is quite nice how everything comes together. Okay, so now we move on. So basically, what have we achieved now? Balls was fine. This is good to know, I guess. But basically, rectangles, we can always assign probability measures to in B of R2. Suppose I give you a joint probability measure in n dimension, or so I know how to then define on all the rectangles, and then I guess I have this theorem which tells me how the measure will extend to Borel sigma algebra and Rn. And now we are saying that we'll also extend uniquely to Borel sigma algebra corresponding to the open sets. So we got all of that worked out. No issues left anymore. Everything is constructed, right? So now we say to ourselves, but we also deal with the countable collection of random variables, x1, x2, x3, and so on, which are IID. Right? We have an infinite sequence of random variables. So now we need to be able to assign probabilities to sigma algebras, on which these random variables, for example, are defined. So random variables we'll talk to later, but right now we'll just talk about assigning, looking at the space R infinity. R infinity is just a sequence of points, x1, x2, and so on, where each xk takes a value in the real line. So that's my space. I collected all these, infinite series of points of real numbers, right? So now the question, okay, how do I define sigma algebra here in a way that later it becomes easy for me to assign probability measure to each of these sets? That's going on in the back of our mind, So, we were able to look at Rn and we saw these rectangles. Rectangles we could put probability measure in, and then we got the probability measure in B of Rn. So we want to do something similar for IID variables as well. You can think of in your mind as, okay, maybe I have multivariate Gaussian variable, x1, x2, x3 are, is an infinite sequence of variables, where for any finite collection, I know what the variance covariance matrix looks like and what the mean value looks like. So how do I now define a probability space where this, where this is the underlying probability distribution in a consistent manner? So that's kind of what we want to do. So what we'll do again, and this is the idea. So these are things which you don't typically see in most books, but this is nicely done in Shiryaev. So Shiryaev is this kind of grand master of probability from Russia. He's, I guess, in mathematics, but the book is filled with errors, by the way. So when you look at the proofs, you wonder what the guy is thinking. It's a completely, the overall structure is correct, but the actual working, it just completely goes bizarre sometimes. So that you have to be careful about. Lots and lots of errors. But it's, but you know what he's trying to do. So it's, yeah, so you figure out. This is this book, I guess. Probability. But he does such a nice job of, defining these spaces and all. So it's worth kind of having this book just for that reason. Okay, so what do we do now? So again, we'll look at rectangles, right? So what we'll do is we'll define these cylinder sets. So interval I1 through IN, product of interval I1 through IN, that's just the idea of rectangle. So all X, where the first n elements are constrained to be in these rectangles. Outside of these n dimensions, they can be on the whole real line. Okay? So we are only constraining the first n dimensions in this. Okay? So let's collect all these cylinder sets, right, with all the rectangles. The point again is these kind of cylinder sets for each n, is n goes from 1 to infinity. We typically know how to assign probability to in a consistent manner. Consistent manner, if we assign a probability to n+1 dimensions and we take a union, so you get an n dimensional cylinder set, they should be matching, the probability should be matching, there should be no contradiction. So that consistency is required. We won't delve too much on it. We just understand that that's not a difficult problem to do. Okay. Now again, okay, you say to yourself, and this is just good to see, I guess. And here you have, and again, you can have all variations of the boundaries. So I'll just collect finite union of all these things, and that's going to be an algebra. Because again, the complement of that will also be a finite union of this sort. Or I can look at cylinder sets of the following form, which is Borel set B1, product with Borel set B2, product with Borel set Bn. So that's how I'm constraining the first n elements, and the remaining just lie in the real line. So I collect all these cylinder sets. So it's obviously bigger class than the first class of cylinder sets. Or I can still do something more fancy. I can just look at all cylinder sets with the first n elements lie in the Borel set in Rn. Right? That need not have this product form B1 cross B2 cross Bn. The point is, with now I'm going to say, okay, let's look at this. So now these two guys here. Okay. So these two guys here are already algebras. You can see. Their complements are also going to be of the similar form. Finite unions are also going to be a similar form. This guy becomes a algebra if I look at a collection of finite union of these guys. Right? Okay. So the point is, at least for this guy, I know how to assign probability measure in a unique manner. So that's a good thing. But all these three guys, if I ask myself, what's the smallest sigma algebra which contains these sets? The smallest sigma algebra is going to be identical. By now, you begin to expect these things, I guess, yeah. But yeah, I mean, just tells you that many of these things are going to be equivalent. So you might as well define sigma algebra on the simplest, and then you're done. Okay, these are all algebras, finite union of type 1 and collections. These are all algebras. We can assign probability to these. So I'm going to call B of R infinity, and this is all from Shirayar. That's the smallest sigma algebra which contains these elementary cylinder sets. These contains sigma algebra, the cylinder sets corresponding to product of Borel sets. The smallest sigma algebra which contains all those cylinder sets. And this corresponds to sigma algebra which contains all the, sets of this form, cylinder sets of this form right here. Where x1 through xn lie in a Borel set in Rn. And we'll argue right now that all three are going to be the same. Okay. So BR infinity, we're going to show is equal to B2 R infinity, and hence we are done. All right. How do we do this? We will collect. So let's define this calligraphic Cn to be all A in Rn such that if I look at all the cylinder sets with x1 through xn in A, that belongs to my sigma algebra beta BR infinity. Right. My BR infinity is going to have a lot of these cylinder sets also in it, right? So let me just collect all A so that first n elements lie in A. That cylinder set is in BR infinity. Now Cn contains all these product of intervals I1, I2 through In. Right, that's how we define BR infinity. It's sigma algebra which contains all these cylinder sets corresponding to these intervals. And then you can see that, okay, this Cn is going to be a sigma algebra. If A is in it, A complement is going to be in it. Right, because then corresponding to A, you get a set in BR infinity. BR infinity is a sigma algebra, so its complement is also going to be in BR infinity. And that's also going to be a cylinder set. And that will correspond to A complement here. And similarly, A1, A2, so on. If these are in Cn, then the union is also going to be in Cn. It's not a difficult exercise at all. You just, these are all the cylinder sets corresponding to A1 and A2. The union of those two cylinder sets is going to be a set corresponding to A1 and A1 union A2 here. And countable union will just have countable union there. So this is a, yeah, so I mean this, you can kind of look at it at a slow pace. So this contains, yeah, so it's a sigma algebra, and it contains these total of these rectangles. So it certainly contains B belonging to B of Rn, right? And since it contains cylinder sets corresponding to B belonging to B of Rn, that, and it's a sigma algebra, that means this is going to be at least as large as B2 of R infinity. So hence it's equal to B2 of R infinity. Okay. Okay. So now, any questions so far, or is this clear? So we started off today by first proving that, okay, you know, we could extend a measure on algebra to a sigma algebra, but we can do it uniquely. Right? If on a sigma algebra we have two measures which agree on a pi system within, then the two measures also agree on the sigma algebra. So hence the extension that we have from algebra to sigma algebra must be unique. You can't have two different extensions. There'd be a contradiction then. So that's how we started. And then we said, okay, now that we know that we have a unique way of extending probability measure from algebra to sigma algebra, let's see how far we can go with that. So on the real line, it's kind of clear now. You know, we'll define probability measures on the intervals, and they will extend naturally to the whole real line. Then we said, okay, what happens with R2? So we'll again define R2 or Rn. We'll define probability measures on these rectangles, and they will extend to the sigma algebra, which contains all these rectangles. And we said that, okay, even if the sigma algebra was defined through open sets, we'll get, you know, it's the same sigma algebra. So we defined everything there as well. So that's a good situation to be in. And then we said, okay, we've done everything for Rn. How do we go to R infinity? And we looked at the cylinder sets, and we defined these rectangles by the first n elements. Right? On these cylinder sets, we can assign probability. And then we said, let's look at the smallest sigma algebra, which contains all the cylinders for all n. Right? So that's what we've done. We'll talk later about how to assign probabilities to these things, but you can almost sense that that will not be so difficult. Okay, and now we say, okay, now let's talk about a bigger space, R of t.
In the previous one, can you once show definition of B1 of R infinity?
So B1 of R infinity was where the cylinder sets were B1 cross B2 cross.
Okay.
Yeah.
Okay. So B1 of R, oh, okay. So these are actually monotonic with each other. I mean, it was, so we, in the next page, we only proved that BR infinity is same as B2 of R infinity, right?
And B1 infinity is smaller than B2 R infinity.
Contained in that, so.
Yeah, it's bigger than BR infinity, so it just fits in nicely. Right, okay. So, and the way to think about maybe T could be that T is, you know, 0 infinity or 0 to 1. So it's a countable set. So we are talking about space of functions, for example, continuous or discontinuous functions. So each outcome is on a functional space. It's a function of T, where T is an arbitrary set, but you know what we have in mind is that T is an uncountable set. So RT is a collection of real functions, xt for T in big T, and typically we'll take T to be 0 to infinity or 0 to 1. Right? So how do we define cylinder sets on this? Anybody? we kind of want to push the idea of cylinder sets now, right?
On some finitely many points,
Yeah.
function value is restricted to B.
Right. Exactly. So we'll just take finitely many time periods, T1 through Tn, and we'll restrict X on those finite time periods. So X of T1 lies in a rectangle I1, X of Tn lies in a rectangle In. Everywhere else, X can take any value, right? From minus R to, from minus infinity to plus infinity. So these are our cylinder sets now. So we'll know how to assign probability to these sets. So there we have to be careful that we should assign probabilities in a consistent manner. There should not be any contradiction that come up. So when we assign probabilities, one needs to talk about Kolmogorov's consistency criteria. So we'll briefly discuss that at that time. But nonetheless, so we've got these cylinder sets. And I mean, now I'm just doing the same thing, but still worthwhile to do the same thing. So, I could have again defined these cylinder sets where I have Borel sets here, B1 through Bn, or I can fix times T1 through Tn and just insist that my xt1 through xtn lie in a Borel set B, where B is in Brn, right? So I can do all these things. And then you say to yourself, okay, let's take a sigma algebra which corresponds to, which includes all of these cylinder sets for all finite collection T1 through Tn, right? So you want to again, say that, okay, this is what we have is the algebra, right? Let me just see. So I T1 through Tn, if I just take a union of these guys, finite union of such sets. So all such finite unions are going to be an algebra. I guess that's correct. Yeah, that part is still true. Right. So I'll assign probabilities to these algebras, and then my big theorem is going to extend them to the sigma algebra. That's the spirit of things. BRT. But what's nice here is as follows. What's elegant in all of this is this theorem right here. So that's why all this is worthwhile. So BRT is equal to B1 RT is equal to B2 RT. But what's interesting is as follows. And this, takes some, you have to absorb this. And every set A in BRT has the following structure. There exists a countable set of points T1, T2, and so on in big T, and a Borel set B in BR infinity. So that every set in this B2RT, so I can actually characterize each and every set in the Borel sigma algebra, in all these three Borel sigma algebra. Each set has the following representation. It's going to be, So each set A looks like X such that xt1, xt2, this countable sequence of x's, lying in some set B for B lying in BI infinity. Right? So that's quite a nice characterization to have, right? It's not immediately obvious. So what do I need to prove? I'm going to collect all these sets A of this form, first of all. And then I'll show that this collection is a sigma algebra. It's clear that this collection is going to include all the rectangles at finite time points. So this collection is at least as big as BRT, right? And then I'll show that each set A belongs to BRT, right? So then the two sigma algebra are equal. My sigma algebra contains all these points, and it's at least as big as BRT, but all of these points are in BRT, so it's equal to BRT. So everybody with me on this? Okay. Let zeta contain all such A sets. Well, actually not zeta, it's calligraphic E. Let calligraphic E contain all such A sets. We'll argue that such a collection E is a sigma algebra. So again, big A is the overall space is a part of this. That's very clear. If a set A is of this form, then its complement is also of this form. Right? It's just X such that xt1, xt2, so on is in B complement. So what I really need to do is, given A1, A2, A3 with corresponding B1, B2, B3, I want to argue that their union is also of this form, countable union. So how do you suggest I proceed?
So countable union of countable thing is countable. So, and take all the B's and also make their union. So you get the thing.
That's right. Yeah. So I'll take all the, so A1 with parameters and set T1 and set B1 with it. I'll let you work out the details on this. This is all in Shreya. A2 has parameters in T2 and the corresponding set in BI infinity is B2. So then union AI is going to correspond to time periods union of TI, and X is belonging to the set union of BI. Yeah. That's right, union of BI. Right. So this will this again has the same structure basically. This union also has the same structure. So it also belongs to E, calligraphic E. So calligraphic E is a sigma algebra. And now I want to say that each such A actually is an element of my BRT. So what I'll do is for that A, I have these time periods T1, T2 through all the way to infinity, right? So all the cylinder sets with finite indices are in BI infinity. Right. Yeah, so how am I going to show this? So what is my set A? It's of this form, right? Yeah. So now if I look at all of the cylinder sets with finite indices T1 through Tn, right? They belong to my BR, my big sigma algebra BRT, right? For any finite this thing. So in particular, the BR infinity corresponding to these indices also belongs to my big sigma algebra BRT, right? But this A belongs to that BR infinity. But this A is
Can you repeat this? Can you repeat this again?
Yeah.
I didn't get it.
No, I'm just saying that let's look at what is this set? This is xt1, xt2, all of these belonging to set B, where B belongs to BR infinity, right? But now if I were to, so I'm just going to look at, I'll just fix my indices T1, T2, and so on. And let me fix them till time n. So then all the cylinder sets with these n indices fixed, right? They are in my big sigma algebra. All the cylinder sets. So the smallest sigma algebra which contains this sigma algebra, that's also in my big sigma algebra. And this smallest sigma algebra contains my set A. Right, because this say at A corresponds to these countable indices. And this B is exactly the sigma algebra I get when I look at the smallest sigma algebra which contains all these cylinder sets. So hence my set A belongs to my BRT. And that's true for each and every A. So we are achieving a lot this way. Yeah? It's a lot of things have been kind of simplified by doing all this. We understand a lot more by seeing this. Agni, any questions? Have you seen this before at all, or?
Not this one.
Okay, good. Shantanu, have you seen this before?
No, sir.
But Shantanu, what's your background? One of the ISIs, or?
Yeah, sir. Mathematics and statistics.
I see. Which ISI?
ISR.
ISI Pune or
Kolkata.
Kolkata? Okay, I see. Is it really Kolkata, or is it far away from Kolkata?
Yeah, it's Kalyani. It's in Kalyani.
It's about 2 hours from Kolkata, right? Really bumpy ride.
Yes, 65 kilometers.
Yeah, which seems much longer. Winter ones. Okay. So anyway, so yeah, you see, I'm playing for time right now, but anyway, just to kind of calm things down a bit. So these ideas settle down. Okay, so BRT, it's very nice that we were able to characterize BRT, but now we realize that all that's interesting in this world is not in this BRT. Because all that depends on more than countably many time periods is not going to be in this BRT. So for example, all the paths xt, which are continuous functions of t, if I collect all those xt's, that set is no longer measurable. It's not in my BRT. It's a very interesting statement, right? Because, if it was in BRT, then we would have given a unique probability measure to it with all the technology that we have. But now we can't give such sets that we want, for Brownian motion, for example, we need to have all these xt's. We need to look at paths which are continuous, because Brownian motion is continuous almost surely. But that set cannot be assigned probability in this manner. So yeah, so it's not that interesting. So that's what we are going to see right now. So for example, let's look at this set A, which is x such that if xt is greater than a, some small a, for all t between 0 and 1. And let's say we are looking at Borel sigma algebra of R01, where our t set is just the interval 0, 1, right? So what about this set A? Is it in our sigma algebra? It's not there, right? Because you can't just look at countably many values of x and determine whether if xt is bigger than a or not. Because you say, suppose a was in BR01, then a will have this form for some countable set t1, t2, and so on, right? Now I can construct my yt as follows, in R01 as follows. Yti is a plus 1 at all these ti points. Okay. And it's equal to a minus for all t's which are not in this set. Now my set A is determined just by observing the values of the function at time ti's. So if you're in this set A, in this ti's, you should be bigger than small a, which is true for yt, for this path yt. But we clearly know that its infimum is going to be less than a. So yeah, there's a contradiction here. Okay, right. So where should yt be? So these are the issues, and the way one resolves this is by defining space. You just define your underlying space omega. For example, you define it to be C01. And this is all the paths which are continuous to begin with. So it's all xt t between 0 and 1, so that xt is continuous. And we know what the definition of continuity is, right? As t gets closer to each other, x of t also gets close to each other. Right? So we'll just restrict ourselves to these paths. Now what we can do is as follows. So this is nice. On this space, we can define cylinder set at finite point intervals and assign probabilities to that. And that will extend to the whole, countable set. But countable set is enough to define probabilities on. By continuity, if you know how the function looks like at a countable set, you also know how it looks like in the limit, because it's a continuous function. You can always approach it through rationals, etc. So what we'll do is, we can define, I guess, rho xy to be supremum, I guess, t between 1 and 0 xt minus yt. Right, this is, so for x and these are for x and y and omega. Right, so this is a distance. What's nice about this distance? Does anybody know on this space? What's a nice property that we get with this uniform distance measure? I guess it should be called L infinity measure, right? So you can actually prove that this space is going to be complete. You know, if we have a sequence of curves which are converging to that curve has to also be continuous. It's a nice, it's an important statement. So it's a complete space in this metric. We'll actually use it to construct Brownian motion at some point. Because Brownian motion that is going to be a limiting process, limit of all the random walks that we discussed earlier. So the limiting process should be continuous. So this will be quite useful to us. Okay, so now you can say, okay, let's construct a sigma algebra on this space corresponding to this metric. So this is a metric, of course, rho xy. That you probably know, right? It's a metric space with this metric. I'm just assuming that you've seen this in the analysis course. Is that right? Or okay, good. Okay, so you can have open balls in this space. You know, each metric will give you open balls, so you can look at the smallest sigma algebra corresponding to open balls, and then you can, you can also have a smallest sigma algebra corresponding to cylinder sets. And what do you think we can show? We can show that both the sigma algebras
Both sides equal.
Yeah. So we'll show the next time. So what we'll do is let's end the class now in a minute or two. I guess we are going a little fast. That's why maybe writing on the board is going to be more fun. You somehow proceed more slowly. Hopefully, the school will open up soon, so we'll start having kind of physical classes. But in any case, what we'll show next time is we'll show that these two, of course, sigma algebra are the same, and then we'll go around and discuss how to assign probabilities to all of these different sigma algebras. Okay, so that's the big picture in all of this, and then we are kind of done with this line of thinking. I mean, we'll still do some measure theory because we have to define Lebesgue measure, Riemann integration, all that, so we can't avoid that. But we'll come to that when we come to expectations, etc. But basically, we'll talk about probability now in this general state spaces. So so we'll go back to doing probability now. But I think with all of this, as well as with the Lebesgue integration and all that, you pretty much know all the measure theory you need to know for probability. So then one can focus on probability ideas. Okay, any comments or?
I had a doubt. So in the uniqueness, where did we use that this measure is finite, like when we proved the uniqueness of the measure?
Well, when we say that A complement, so because we have to show that B minus A is, I think, so P1 of B minus A is equal to P2 of B minus A. No, so P1 of A complement is equal to P2 of A complement. So that's P1 of whole space minus P1 of A, minus P2 of whole space minus P2 of A. So if the P1 of S was not finite, then you were Okay. All right. So there are a variety of books that you can look at. Royden is a very good book for these things, for measure theory in general. At least the first argument which I used over the pi system was essentially from David Williams, Probability in Martingales. This part I'm talking to you right now is from Shiryaev. But I'll be jumping across these books and then I'll tell you what other books I use for other things. Okay, so there are quite a few books, but I guess it it's good that you get exposed to all these books. It should not be a problem. Okay, so if there are no questions, I'll stop the recording. Okay, so we'll meet next Wednesday. Actually, we can chat a little bit right now. Yeah, time.